Case Western Reserve University's Great Thinker Series proudly presents the Origin Science Scholars Program. These lectures are presented by the Institute for the Science of Origins, a partnership of Case Western Reserve University, the Cleveland Museum of Natural History, and IdeaStream, with the assistance of Case Western Reserve University's Siegel Lifelong Learning Program, the College of Arts and Sciences, and MediaVision. It's my pleasure tonight to welcome a colleague and friend. Andrew Tolley did his undergraduate work at Oxford University and then his PhD at Cambridge University. After that, he crossed the Atlantic to this side and spent some time at Princeton University for postdoctoral work, and then was a distinguished research fellow at the Perimeter Institute in Canada. From there, he joined us here at Case Western Reserve University in the Department of Physics, where he is an associate professor in the Particle Astrophysics and Cosmology group. And tonight, he will tell us about from Newtonian gravity to Einstein's theory of general relativity. Please welcome Dr. Andrew Tolley.
So I shall be attempting to introduce to you Einstein's theory of general relativity. For those of you that don't know, this year is the 100th year of this theory. Einstein completed the theory in 1915. And all physicists would agree that this is still one of the greatest scientific achievements of the 20th century. And I'm going to try and explain to you a little bit about this theory. But we're going to start basic, and we're going to start with Galileo and Newton and what was understood by Galileo and Newton. And then we'll slowly see how Einstein's developments and those of others through special relativity eventually led to what we now call the general relativity, which is the current understanding of the theory of gravity. So let us begin at the beginning. So in fact, many of the foundational principles of our current understanding of what gravity is can be traced back to Galileo. And there are two key concepts, and whilst these weren't the names given by Galileo, you can see these concepts in Galileo's work. As what we now call the equivalence principle. There's the first one, and the second one is the concept of relativity, as according to Galileo. So to the first concept, Galileo was concerned with how objects fall under gravity. And as most of you probably know, there was a belief at the time that came from Aristotle that heavier objects would fall faster than light objects. And Galileo gave a very interesting thought experiment to show why this couldn't be the case, or at least he believed couldn't be the case. And so he said, well, imagine two objects, one light and one heavy. So here's a big heavy object, a big heavy ball, and a light one, and you attach them together via a string. Now, if Aristotle is correct, then the heavier object will fall faster under gravity than the light object. And that will make the string between them taut. But once the string is taut, you can then think of that as a single object whose mass is the sum of the individual masses of the light ball and the heavy ball. But then if Aristotle is correct, then that combined object would fall even faster than any of the individual components, which is obviously a contradiction. So by that reasoning, Galileo argued that Aristotle must be wrong, and it must be the case that heavy objects fall with the same acceleration under gravity as light objects. And then that led to his famous Tower of Pisa thought experiment. No one knows if he actually did it or not, but he proposed a thought experiment where you stand at the top of the Tower of Pisa and you drop off two objects of different masses, and if you neglect arid resistance, then they will fall with the same acceleration towards the Earth determined by gravity, which in the Earth is locally, that acceleration is given by this number 9.81 meters per second squared. And we now know that really to be the right answer. So that's the first thing, and this will come back later as very important to Einstein's thinking about gravity. But now let's come to the second one, which is the concept of what we would now call relativity. We find this already in Galileo's work on the dialogue concerning the two chief systems of the world. And here's the text. I'll read it for you, but it's a little bit small. But it starts off, shut yourself up with some friend in the main cabin below decks on some large ship, and have with you there some flies and butterflies and other small flying animals. Then he goes on to sort of talk about various experiments you can do with the flies and butterflies. So this is very poetic language relative to modern papers, but this is how he described it. And then we get to the crucial point. When you have observed all these things carefully, i.e. you've done experiments with flies and butterflies and fishes, though doubtless when the ship is standing still, everything must happen in this way, have the ship proceed with any speed you like, so long as the motion is uniform. So now the ship is moving and not fluctuating this way and that. And you will discover not the least change in all the effects named, nor could you tell from any of them whether the ship was moving or standing still. So what Galileo is saying is if you're in a moving ship inside and you're not looking out the window, if that ship is moving at constant velocity, you can't tell you're in a moving ship. Everything locally to you looks identical to what if the ship was at rest. And that's really the concept, what we now call the concept of relativity. And to understand why that is true, let's think about throwing a projectile initially at some constant velocity in the horizontal direction, which then falls under the gravity. In the horizontal direction, if it has some initial velocity, it just keeps that velocity, and the velocity it has in the horizontal direction is not affected by gravity, but in the vertical direction, it'll fall under gravity, and it'll create this parabola. But the key thing is, whilst gravity affects how it falls vertically, it doesn't affect how it moves horizontally. And so now let's imagine those two ships of Galileo. Here's one ship, the ship is at rest, and someone inside the ship just drops a ball to the earth, and it'll fall under gravity. It'll accelerate down with a constant speed that's independent of its mass. And then you have another ship which is in uniform motion at some constant velocity. And imagine that someone on that ship then also drops the ball. Well, from the point of view of the ship at rest, the initial velocity of the ball will be a constant velocity because the person on the ship that drops the ball himself is moving at constant velocity, the velocity of the ship. And so the ball will drop with a parabola, but as the ball drops with the parabola, the ship is also moving along. And so then what you get is in the rest frame of someone who's sitting on the ship, they don't see anything moving in the horizontal direction. All they will see is the ball drop directly downwards as if the ship was at rest. And that's the concept of relativity. And so by reversing that argument, in the rest frame, what we call the rest frame of the observer who's inside the moving ship, they will, from their point of view, the ship that used to be at rest is also in motion in the opposite direction, and the reverse of that argument is true. So this is the concept of relativity, that motion, uniform motion is relative to the observer. So we say that motion is relative, and all observers who are in uniform motion are equivalent. The fancy way of saying that in modern terms is that we call each observer who's moving at constant velocity an inertial frame, or inertial frame of reference, and we said that the laws of physics are the same in all inertial frames of reference. So he summarized that in a bit of poetic language again. So the fish in the water will swim towards the front of the bowl with no more effort than towards the back, and will go with equal ease to bait placed anywhere around the edges of the bowl, and so on and so on. So this is the concept of relativity, according to Galileo. Now, in the year Galileo died, Newton was born, and Newton incorporated into his famous laws of motion Galileo's concepts, and in particular in Newton's first law, which is written here in the Latin. Newton's first law says, every body perseveres in its state of rest or in uniform motion in a straight line, unless insofar as it is compelled to change that state by forces impressed thereon. So in more ordinary terms, he's saying if there is no force, if an object is initially at rest, it stays at rest. If it's initially moving with constant velocity, it stays at constant velocity. But that has to be true because of Galileo's notion of relativity. Because if something is initially moving at constant velocity, you can't tell if it's at rest, because in somebody else's frame, that object is at rest. And if the object is at rest and you don't put forces on it, it's going to stay at rest. So Galileo's concept of relativity is built in to Newton's first law, and what is often called the concept of inertia. So inertia is essentially the name for this property, that something that has some velocity, some speed, will continue with that velocity unless acted on by a force. And furthermore, in Newton's second law, the famous one that determines how forces create acceleration, in fact, really it's the key that forces create acceleration and not velocity. So acceleration is the speeding up or slowing down of forces, which is the same according to all Galilean frames of reference. So all observers will see the same acceleration, even if they don't agree with the velocity. And furthermore, Newton's second law tells us that the larger the mass of an object, for the same force, the smaller the acceleration. And then tying that together with Galileo's argument that all bodies fall to Earth, regardless of their mass, they'll fall to Earth with the same acceleration under gravity, then the only way that can be true is if the force of gravity itself is proportional to the mass of the object. Essentially so that the mass here cancels out in this formula so that you get that the acceleration is a constant independent of the mass. And now we call this the equivalence principle. In modern language, this is saying that the effective mass seen in gravitationally, the thing that determines the strength of gravity is the same as the inertial mass that comes in Newton's second law. And again, this will become important later. Now, to complete Newton's story, if you posit that the force is universal, so let's think about an apple falling to the Earth. So we know that the force, to explain Galileo, is prediction that everything falls with the same acceleration, then the force of gravity on the apple from the Earth must be proportional to the mass of the apple. So it cancels out in Newton's formula. But by the same token, the force from the apple on the Earth, not something we tend to think about, must be proportional to the mass of the Earth. But this is the same force. There's only one gravitational force between the two. And so you infer that the force of gravity must be proportional to both the mass of the apple and the mass of the Earth. And so in other words, it's proportional to the product of the mass of the apple and the mass of the Earth. And then there was only one missing piece, which is how the force of gravity changed with distance. And in fact, several scientists, including Hooke and Bolyaldus, suggested that the way the force of gravity depends on distance is an inverse square law. So that means as you double the distance, you decrease the force by a factor of 4. And Newton showed that if that were true, then you would precisely predict what were known to be the Kepler's orbits of planets around the sun would be a direct consequence of that inverse square law. And so he put it all together, and this gave him his final form for the force of gravity, that the force of gravity is proportional between two objects of a given mass, is proportional to the product of their masses, and inverse square of the distance between them. And there's some constant in there, which we now call Newton's gravitational constant in that formula. And interestingly, Newton himself was the first to even question his own theory. It was a nice theory, but he could see there were some problems. One of them was that this notion of action at a distance, regardless of how far those objects were away from each other, the force of gravity is always acting. And so he said that one body may act upon another at a distance through a vacuum without the mediation of anything else, by and through which their action and force may be conveyed from one another is to me so great an absurdity that I believe no man who has in philosophic matters a competent faculty of thinking could ever fall into it. But of course he did fall into it. So that's my summary of Newtonian gravity. And the key points are Galilean relativity. We'll see how that comes back later in Einstein's thinking. And Galileo's famous recognition that all objects will fall to the Earth with the same acceleration, regardless of the mass, at least if you neglect air resistance. And then Newton had it that gravity was a universal force. He had one formula that always described the same force, which was proportional to the product of masses of the two bodies and inversely proportional to the square of their distances. But there is a bizarre thing about this force, as Newton recognized, that it's action at a distance. So no matter how far away two objects are, they will always feel each other's influence instantaneously.
Galilean relativity all this time, how come Einstein gets all the credit for relativity? It's a new thing.
That's a good question. So I think people forgot, at some level people forgot how much Galileo saw as well. But I think it's also partly because now Einstein's relativity is an important, it has a different flavor to it, and what we really remember is the significance of that discovery. Yeah, but relativity really is Galileo's idea, and you see clearly stating that concept.
So Hooke used to complain that Newton had stolen the idea from him. Is there?
That's right. So when when Newton presented this at the Royal Society for the first time, his complete formula, Hooke was there, immediately accused him of plagiarism because he had himself thought of the inverse square law as well, as in fact many other people had done. But Hooke did recognize what Newton got credit for, and why he got credit was the calculation of these Keplerian orbits, which Hooke hadn't done, at least with any the same level of accuracy. And that's why we remember Newton for gravity, even though, of course, he did not invent gravity. He did not even get all the details. He was not even the first to think of all the details of the force, but he was the first to convincingly demonstrate that this was the only formula that fit the astronomical data at that time.
Thank you for joining us. You've been watching Dr. Andrew Tolley discussing Galilean relativity and Newton's gravity. For more information on the Origins Science Scholars Program, please visit the Institute's website at origins.case.edu. In the next part of the talk, Dr. Tolley discusses special relativity. Now, back to the talk.
Okay, so the second part is we're going to fast forward in time to really the end of the 19th century. And up to then, these notions, Newton's laws of motion, were not questioned, and Galilean relativity was not questioned. To the late 19th century, the 19th century physicist was concerned with the nature of heat and thermodynamics, and also the crucial question of what are electricity and magnetism. And what electricity and magnetism are was answered by James Clerk Maxwell. There were many parts of the theory that were built up over time, but he was the first one to write down the complete description of electricity and magnetism and unify it, in fact, to a single theory of electromagnetism. And this really was one of the towering achievements of 19th century physics, and it fit all the observations of what you needed to describe electric fields and magnetic fields and the motion of charged particles and so on. In his famous paper in 1865, he also predicted the notion of electromagnetic waves. So these were waves in which the electric fields and the magnetic fields were oscillating in space and time, a lot like water waves. And he calculated the speed using his theory, and he found that the speed was extremely close to what was understood to be the measured speed of light at that time. And so, of course, it became very natural, and I think Faraday first suggested this, or had suggested it before. It became very natural to associate those electromagnetic waves with light itself. And you see here he's saying the agreement of this result seems to show that light and magnetism are affectations of the same substance. And again, this is something we now know to be the correct answer. And a few years later, electromagnetic waves, clear evidence that the light and radio waves and so on were electromagnetic waves was given by several people. However, the problem is, and it wasn't clear at the time, but it was clear in retrospect, is that Maxwell's equations violated Galilean relativity. So that means that they didn't have this property that couldn't be the same in all different Galilean inertial frames of reference. So if you're using Maxwell's equations in the ship at rest, you'll get a different answer than if you used it in the ship moving at constant velocity. And so there were two solutions to this, and the one that Maxwell chose was the first one, is that you should only apply his theory, his equations, in one particular preferred reference frame. And that reference frame, he supposed, was the reference frame of some fluid that filled space and time that was called the luminiferous ether. There's another solution, which of course is the right answer we'll get to, is that Galilean relativity must be modified in some form. But the first one is the one that Maxwell took. And what they imagined, and it's amazing in retrospect that this was the general perspective, but people imagined that there was space and time were really filled with some fluid that had to be stiffer than granite in order to determine the correct speed of light propagating through it. So there's fluid called the ether, in which the light was a wave inside this ether, and it had to be stiffer than granite, but it had to be perfectly inviscid, which basically means that nothing interacts with it. So as the Earth goes around the sun, it's going through the ether, but nothing happens to it. So this is a sort of crazy concept. How can something be so stiff but have no viscosity? Anyway, that's what he proposed. in fact, many other people proposed that at the same time. And so people went to look for the motion of the Earth through the ether, because by that point, of course, no one thought the Earth was at rest. People knew the Earth was moving. And so if it's moving, it must be moving through the ether. And so we should be able to detect the actual motion through the ether by the modification of the propagation of light. And of course, there were many experiments to look for this, and this is, of course, the most famous one right here at Case, which is the Michelson-Morley experiment, which was a particular type of optical experiment, an interferometer, that was intended to figure the speed of the Earth through the ether by the fact that if the Earth was moving, then the experiment was moving. Then if the light went down this way versus this way, in one path it would have to go longer than the other, and you would see then by combining the two together and looking for interference, you would be able to figure out the velocity of the Earth. And famously, it gave a null result. They couldn't find any motion of the Earth through the ether. And this was a significant problem, and many physicists attacked this to try and understand. And so it was first George Fitzgerald who proposed a rather crazy idea that when objects move through the ether, they somehow become contracted. So their size becomes changed as they move through the ether. And this he argued, could be used to explain they were contracted in precisely a way to cancel out the effects you would see in this experiment, so you wouldn't see any interference pattern. And this was developed into a complete theory by Lorentz and, well, really finally by Poincaré, who put it all together. And the idea that Lorentz had was that as you move through the ether, you have a different notion of space and a different notion of time. So something that's moving through the ether will have a different, we'll see space differently and we'll see time differently. They'll measure different time on a clock in such a way to cancel out any effects in these experiments that we're looking for the ether. So this is a slightly bizarre thing. So things change as they move through an ether so that you can't ever find that you have an ether. That was what they were positing. And Einstein just turned it round. He didn't really give any new mathematics. Lorentz and Poincaré already had the mathematics. He simply said, well, if you're creating these crazy formula to try, and the notion that things change in their length and so on, and time is different, to say that to explain why we never see our motion through the ether, maybe the ether just isn't there. And of course, that is the right answer. And in fact, what Galileo did, what Einstein did, is reintroduce Galileo's concept of relativity, that all inertial reference frames are equivalent, so that as we move at constant velocity, then the laws of physics should still be true, and so Maxwell's equations should apply in the ship at rest and should apply in the ship moving at constant velocity. But of course, he still needed to explain these experiments, and so like Lorentz and Fitzgerald and Poincaré and so on, he still had to imagine that space and time measured by observers who are moving at different velocities would have to be seen as different things. And so we return to Galileo's experiment, and here we think about the two ships again, and some object moving, described by some position in the horizontal direction and the vertical, and some time t. And now let's imagine a moving ship. In the reference frame of the moving observer, the same space and time will get modified through this complicated formula with square roots here and so on, which depends on the speed of light. Now, don't worry too much about the precise formula, but it's clear that this formula is much more complicated than Galileo's formula, and it describes how an observer moving at some constant velocity will measure differently space, x, y, and time, t, relative to an observer at rest. And these are what we now call Lorentz transformations. By the same token, through these transformations, he was able to show that Galileo's notion of relativity is still true. In other words, if you go to the reference frame of someone who's locked up inside the hull of the ship, then they will not know that they're moving at constant velocity, and they will see what's going on in the other ship they will see basically different notions of space and time relative to that. And all this happens in a rather magical way, so that for the two observers, so observer 1, you can think of the ship at rest, and observer 2 is the ship moving at constant velocity, they measure space and time in a different way, such that they always agree on the speed of light. And that's the property of the Lorentz transformations. And in fact, what Einstein did was to derive those transformations based on assuming that all observers, no matter what their velocity is, will see light to be traveling at the same speed. So this was quite a radical concept, although it was the only thing that was consistent with Maxwell's equations. And so here, to emphasize this point, here the picture is if someone is on the moving ship and they shine a torch, then light goes out at the speed of light. According to Galileo, from the reference frame of the ship at rest, then that light should be going at faster than the speed of light, because you'd think it would be the speed of light plus the speed of the ship, so you'd think it'd be going faster. But according to Einstein, the speed of light from this torch is also the speed of light in vacuum, the same speed, even though this guy's at rest and this ship is moving. But to achieve that, he had to imagine, as Lorentz and Fitzgerald had done, that space and time measured by different moving observers are different. And it was his professor, Hermann Minkowski, that tied this together and recognized that really what was going on is that space and time were not separate things, but should be wedded together in terms of a four-dimensional space-time geometry. And he delivered a nice address in which he says, "The views of space and time which I wish to lay before you have sprung from the soil of experimental physics, and therein lies their strength. They are radical. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve in an independent reality." And he was exactly right. And to explain that, I need to tell you a little bit about geometry and remind you for what we mean when we talk about two-dimensional geometry. That can be summarized by Pythagoras' theorem. If we're in 2 dimensions and we want to measure the distance between here and here, and we do so by doing a triangle like that at 90 degrees, then the distance from this point to this point is given by, that distance squared is given by the sum of the squares on the other side. And that's Pythagoras' famous theorem. And that theorem basically encodes what we mean by a 2-dimensional geometry. And then later that was generalized to the notion of 3 dimensions. We all know we're in 3 dimensions of space, this way, and this way. And to compute a distance in 3-dimensional space, then you take the distance. If you have a cube, for example, you want to know the distance between here and here. You take the square of the sum of each of these 3 sides, and then that is equal to the square of this distance. So this is essentially just Pythagoras' theorem in 3 dimensions. So what do you do when you get to 4 dimensions? Well, you just do it again, except now there's a twist. And the twist is that you put in a minus sign here, and it's that minus sign that distinguishes between space and time. But nevertheless, this is a 4-dimensional geometry in which to compute the distances between 2 points in space and time. You just use Pythagoras and you add up the 4 things, except you don't add them all up, you minus the amount in time, multiplied to get the units right by the speed of light. And here's a copy of some notes from Einstein, I think around 1913, in which you show him clearly having taken in this concept, and when you've got 4 coordinates here, x, y, z, I, c, t. This is the time direction with a square root of -1 in here. That was Minkowski's notation. And you see him clearly using that concept. Now, a key feature about this is that space-time geometries are very different than space geometry. So whilst we're saying that we have a 4-dimensional space, a 4-dimensional space-time is something quite different. It has extra structure because of that minus sign. That's the only difference. It's the only difference we know of between space and time, that minus sign there. It has a big influence because it means that sometimes the distance between things in space-time is positive. Its distance squared is positive. Sometimes it's negative, and sometimes it's 0. And the cases where it's 0 are precisely for things moving at the speed of light. And so here is a picture. Imagine a point, and you imagine you send out a light beam that could go in any direction. This is a picture of that light beam moving forwards in time, and here's a picture of it going backwards in time, if you could imagine that, or you really mean the light coming in, converging to that point. And that creates something called a light cone, the cone of light propagating from a point. And along any point on that cone, the distance between here and here in space-time is 0. This light cone distinguishes, so in relativity, it's also true that nothing can travel faster than the speed of light, essentially because of this formula. And so the light cone separates those points that you can reach from this point by traveling at slower than the speed of light, and similarly backwards in time, those points that can reach here by traveling slower than the speed of light. And so those are what we call that's really the future. In other words, those points that we can influence through interactions. And so here we have the future, and here we have the past. That's the region of space and time that can influence us. And then there's a whole other region that's neither the future nor the past, which we cannot interact with because it would require something traveling faster than the speed of light to reach that point. This kind of geometry is much more complicated than what you would get if you had a four-dimensional space geometry. But it was really this geometry, Minkowski's recognition was that relativity would just the relativity was telling you that we really lived in a space-time geometry, and space and time are wedded together in this way, and we should really from now on not compute the distance of things and the time of things, but we compute the distance in space-time according to this formula. So in summary, the key recognition of Einstein is that the ether, the luminiferous ether that people imagine that light was propagating in, did not exist, and that Maxwell's equations really are true in all frames of reference, all inertial frames of reference, or all reference frames in which you're moving at constant velocity. But to explain the null results of the Michelson-Morley experiment and other experiments, measurements of space and time had to be modified in a way that they're relative to the observer. So not everyone agrees on how long something takes in time. Not everyone agrees how long something is in space, but everybody agrees on the length in space-time according to that particular formula. And all this works in a magical way such that the speed of light is the same in all frames of reference. And so this is really the key recognition from special relativity, is that we really do live in a four-dimensional geometry.
Don't you have to say the Earth is moving with respect to something?
That's right. So the motion is relative. That's right. So that's what the ship experiment is telling you.
So I'm not moving.
So you're not moving if you're moving at constant velocity relative to someone. But if you're accelerating, then you are moving, because everyone will agree that you're accelerating. So the motion is relative only for what are called inertial observers, those moving at constant velocity. Yeah. But you can always change to the frame of reference in which you're at rest. Yeah.
So what does it mean that the Earth is moving around the sun and not vice versa?
So the question is, what does it mean that the Earth is moving around the sun and not vice versa? And in some sense, it's true that I can go to the frame of reference of the Earth, and I see the sun moving around me, or vice versa. I can go to the frame of reference of the sun and move around, and the Earth is moving around me. And neither are wrong, but both of those frames are not what we call inertial frames. So the concept of special relativity actually doesn't apply in those particular frames, because they're really, there is some acceleration going on, and that there's gravity involved, and that really then we have to go to general relativity, which is the next section. So in reality, the Earth and both the Earth and the Sun are really moving around the center of mass of that solar system, but the center of mass is in turn moving around the galaxy, and so on and so on. So motion is always relative, but there is a difference between constant velocity motion and accelerated motion.
So the big finding was that the speed of light is constant and everything else had to change to accommodate that. And that's all from Michelson-Morley's experiment here, or other people also
That was the most
confirmed
definitive experiment showing that. There were many experiments done around the same time, different types of experiments looking for the motion through the ether. But that was the most definitive experiment that really gave the conclusive evidence that the speed of light was the same in all frames of reference. Yeah, and that was certainly influential in Lorentz's thinking and Fitzgerald's thinking. We don't know how influential it was in terms of Einstein's thinking.
Weren't there some experimenters said they found something goes faster than light a few years ago, or?
Oh, yeah, the question was, were there some experiments measuring faster than the speed of light, or I guess to translate, maybe measuring the motion through the ether, and I'm sure there were, but those effects always went away on further detailed measurements, yeah, so I'm sure that I haven't looked at the history of that too much, but I'm Usually that's the case. Oh, recently?
Recently, the particle accelerator or something?
Oh, no. To date, there is no violation of special relativity that we know of. Yeah. So that's right. Oh, there was a recent statement about neutrinos possibly traveling faster than the speed of light, but that went away on. That turned out to be an experimental error.
We hope you've been enjoying the Origin Science Scholars Program with Dr. Andrew Tolley. Dr. Tolley was awarded a Faculty Early Career Award by the National Science Foundation to fund his work on the nature of gravity. In the second part of our talk, we learned about special relativity, Einstein's theory describing the behavior of fast-moving objects. In our final segment, Dr. Tolley will discuss general relativity, Einstein's theory of gravity. Now, back to our talk.
Okay, so I'll move to my third part, which is general relativity. And this was Einstein took about 10 years to reach this from special relativity, which at some level gives you an idea of the conceptual leap that went going from special relativity to general relativity. But let's start off and let's think about repeating Galileo's experiment. Einstein did it with this elevators, but let's think about doing ships. So let's imagine you put a ship up there in space and then you drop it down. It's under free fall, under gravity. And this is where Galileo's concept of the equivalence principle comes in. We know that everything falling under gravity, if we neglect air resistance, will fall to Earth with the same acceleration. So if an observer is inside the hull of the ship and they drop the ball, the ship is falling down with a given acceleration, and the ball is falling down with a given acceleration. And so, of course, the ball does not fall down with inside the ship. Relative to the ship, the ball of it on the right-hand side remains a fixed position. Whereas for the ship, which is on the sea, you drop a ball, and of course, it just falls down with fixed acceleration. So now what we're doing is we're thinking about going to the reference frame, the accelerated reference frame, what we now call the free-falling frame, the ship that's falling downwards. And in the free-falling frame, you drop a ball, and it doesn't fall downwards. It just stays there. So in some sense, there is no gravity inside this frame. That follows because of Galileo's equivalence principle. So locally, you just don't feel any effect of gravity because nothing moves down. Of course, from the outside observer's point of view, it's because both the ship and the ball are accelerating downwards. But if you're inside the ship, I'm allowed to work in the frame of reference of that observer, you don't see any effect of gravity. And of course, this is an experiment we can actually do now. And so it leads to the concept, if you're in an accelerated frame of reference, i.e. you're in free fall towards the Earth, you just let yourself go under gravity, that's locally equivalent to being at rest without any gravitational field. It's the concept of free fall. Or reversing that, if you're at rest in a gravitational field, so you're sitting in an elevator that's on the Earth, that's locally equivalent to having an elevator which is accelerating upwards. As the elevator accelerates upwards, you'll effectively feel a force that you'll attribute to gravity, even though it's really just acceleration. So it was this recognition that there was something equivalent between acceleration and gravity, and also the idea that you can somehow get rid of gravity by just changing to an accelerated, i.e. a free-falling frame of reference, that was influential in Einstein's thinking in the development of general relativity. And so let me say that more concretely. So at every point in space and time, if you're in a gravitational field, we can always go to the frame of reference of someone who is free-falling. Okay, so just let them fall under gravity and not stay where they are. And locally, for each of those people, it's as if they don't feel any effect of gravity. They feel themselves just to be at rest. So if you're inside an elevator, so you can't see out, or you're inside a ship, so you can't see out, then you don't know that you're in a gravitational field. However, so to see where the notion of curved space-time comes from, we're saying that locally we don't feel any effect of gravity, but each of those frames of reference, each of those locally free-falling frames of reference have to be patched together in some particular way. And the way they get patched together is not entirely perfect, so they don't exactly align up with each other. So here's a patchwork quilt to sort of give that idea. So at each point in space, each one of these patches represents a free-falling frame of reference where there is no gravity. So where the gravity really is in how these different patches patch together. And this leads to the notion of a curved space-time. A curved space-time is when this patch doesn't quite fit up with the next patch and doesn't quite fit up with the next patch and so on. And so as you move along this space-time, you get rotations and movements and so on. And this is how you can understand, this is how Einstein understood how planets move around the sun, why they move on elliptical orbits, and why light is bent by the sun. Because really the light is always traveling in a straight line in a local patch, in a local free-falling frame of reference. You see it's moving on a straight line here, and a straight line here, and a straight line here, and a straight line here. But where the curve comes from is the fact that each of those local patches don't quite match up together. Now in reality it's something much more smoother than this, but this gives the idea. So as the Earth goes around the sun, it's actually moving along a straight line. But we don't see it as a straight line because the space around the sun is patched together in a curved way that creates the curvature. But locally, the Earth and also light bending around the sun is always moving in a straight line. And so it's the geometry that gives rise to gravity in this picture. So here's another example of a curved space-time. So if you go to the Peter Lewis building, each individual, you can make up this curvy building here, but each individual brick is basically an ordinary brick, and what makes the curvature is how you fit them together. So you think of each individual brick as one of these free-falling frames of reference in which an observer in that frame of reference sees no gravity, but where the gravity really is in how they get patched together and how you create that curvature of space-time. And so one of the predictions of general relativity was that because of this space-time curvature, light would, a massive object like the sun would bend the passage of light around. And in fact, also Newton's theory would predict that, but Einstein's theory predicted that the angle that it would bend as the light went around the sun would be twice that of Newton. And that was one of the first distinct predictions of Einstein's theory relative to Newton's theory. And people went out to look for it specifically. Sir Arthur Eddington went out and looked at the solar eclipse of 1919 and looked at how the position of the stars got moved during the eclipse to see precisely the change in position because of the light being bent around the sun when the sun was within the path. He gave the first evidence that this really did occur from that, and this immediately catapulted Einstein to international fame. And now this effect, which we now call gravitational lensing, so the fact that massive objects curve space-time and therefore can act like a lens in the sense that light passes through curved paths, is now something we observe every day, both from stars and galaxies and even clusters of galaxies and the whole the cosmological scale. So this is the key realization of Einstein, is the equivalence principle led him by a long chain of reasoning to the notion that space-time is really a curved geometry, and but you build up a curved geometry by patching together locally flat geometry. So each of like those bricks in the Peter Lewis building. So locally it looks flat, and you compute the distance between 2 points locally. But how you compute the distance over here is different than here, is different than here, and is different here. And that's how you encode the geometry of space-time. And we do this through something called a metric, which is a 10-component object, which describes basically how you change your rule, how you change Pythagoras' theorem to describe a curved space-time geometry. But all it is an instruction rule to say, if I'm at this point in space-time, how am I supposed to compute a distance in space-time, given a distance in space and given a distance in time? And I do it one way here, but I do it a different way over here, and I do it a different way over here. And it's that rule for how it changes that describes the curvature of space-time. And that in turn then describes gravity itself, how objects will move through the curved space-time. So this is a very sophisticated concept, but it's now well tested that this is the current best picture for what gravity is. So you might conclude that from the equivalence principle that you can't really ever distinguish between being in a gravitational field and an accelerated frame of reference. That's how I told it to you so far. Well, that's sort of true at 0th order, but it's not really true if you're a bit more careful, because you can feel the effect of gravity through tidal forces. And here you see that's basically because in a real gravitational field, things move, say, if you're in the Earth, things move towards the Earth. And so these two objects, if they're in an elevator falling towards the Earth, they're going to get slightly closer together because they're moving towards this point. And so, and more generally, if say, an astronaut is falling towards a heavy object, like a black hole or something, they'll become stretched by the gravitational field. And so it's those tidal forces, the stretching type forces, that you can actually use to measure the local curvature of space-time. And in some sense, this is the real part of gravity, these tidal forces, rather than not just this sort of constant acceleration down. And so general relativity leads to many weird and wonderful predictions, such as black holes. Here is a geometry of black holes. A black hole is a space-time which is curved so much. There is a region of that space-time where light simply can't get out because the gravity is so strong, and there's a very clearly defined distance from the center of the black hole, which we call the event horizon, that describes that. And around the black hole, the space-time is curved in this complicated way, given by, in this case, this is a particular metric. And here's a picture of a black hole, a diagram representing a black hole. Here's space going along to the right and time going up. And here you think about matter. There's some star that collapses to form a black hole. Here's the collapsing matter. There's no black hole at this point. And then as you go forwards in time, eventually at some point the black hole forms. And you have this radius, which is called the event horizon, out of which light can't escape. And the reason light can't escape is what's happening is that here, the space-time curvature is represented by the bending of these different light cones. So this is the local light cone you can think of as the local free-falling frame of reference that describes the way, which way light will move. So this is the future, this is the past. Future, past. And the light cones get bent by the gravitational field such that at the event horizon, you see they're tipped in such a way that the future, any light sent out at the boundary of the event horizon will only ever go inside the black hole and never outside. And so it's that bending of those light cones that is what is responsible for the fact that black holes are black in the sense that they have this event horizon. And one of the other great predictions of general relativity, which came pretty early on, was noted by several people, Freeman, Lemaitre, Robertson, and Walker, is that because of the equations of general relativity, this notion of curved space-time, the universe should be expanding, or it should be expanding or contracting, one or the other, but it's essentially it should be becoming either more curved or less curved with time, and the right one is that it's actually becoming less curved with time. And you can think, and you can describe this geometry in very simple terms as a simple modification of Pythagoras' theorem, in which you, at each time, t, you compute the distance and you multiply it by some number, and that number changes with time. So as you go into the future, you use a bigger number, and so that's effective as saying that space is bigger. But really what it is, it's like this. I say, at this time, this distance is, say, 3 centimeters, and then at a later time, I say it's 4 centimeters, and then a later time it's 5 centimeters, and so on. And what's really happening is that this region here is becoming more and more curved, and I should change how I compute my distances. And that's how we understand that the universe indeed is expanding, and this was famously the famous observations of Hubble, which showed that galaxies were moving away from us because the light from them was redshifted, confirmed that expansion, which had effectively been predicted theoretically already at that point. And so here are the final equations. And obviously I'm not giving you the full details, but here is the sort of transition from Newton's equations to Einstein's equations. In Newtonian theory, the force, gravity really is a force, which is given by the product of masses, a Newton constant divided by the distance squared. In Einstein's equations that you have to solve to determine these metrics, they amount to essentially, there are 10 equations for 10 unknowns, this metric which measures how Pythagoras' theorem gets modified, but they amount to simply saying that the local curvature of space and time is proportional to the density of energy and momentum and so on. So, so in summary, the equivalence principle tells us that locally the effect of gravity can be removed just by changing frames of reference, changing to a free-falling frame of reference. But where gravity remains is in the notion of how those frames of reference patch together. In other words, how you build up a particular curved geometry from patches which are locally flat geometries. And space-time curvature gives rise to tidal forces. And Einstein's theory tells us that the amount that space and time is curved is proportional to the local density, energy, momentum density, and stress and pressure. And we'll hear more about the predictions of general relativity next week from Professor Durant. So I'm going to end there.
This lecture is part of the Origins Science Scholars Program of the Institute for the Science of Origins, a partnership of Case Western Reserve University, the Cleveland Museum of Natural History, and IdeaStream. It has been brought to you with the assistance of Case Western Reserve University's College of Arts and Sciences, Siegel Lifelong Learning Program, and MediaVision. For more information on the Origins Science Scholars Program, including a full video archive, please visit the Institute's website at origins.case.edu.